So QS corresponds to the remainder. At the end, you will be having quotient in Q, remainder is in A, right? So QS corresponds to the sign of the quotient, which is AS XOR with BS. XOR operation of your sign. And because dividend sign is minus, divisor sign is plus, then quotient sign obviously up minus only, right? If dividend sign is plus and divisor sign is minus, even then the quotient sign will be minus. If both are same, it is plus. So XOR operation of the respective signs will result the quotient sign. Okay. So first of all, we have to during a division, see how many number of bits are there in B, right? So that many bits from the dividend are considered, and whether it is subtracted by one time or not, that we will check by doing A minus B initially. Okay. So a number of bits in B and number of bits in A are same here, because the A, B, Q are three registers which are of same length, which are of n minus 1 bit length. Okay. So A minus B will happen. Okay. That results E and A. How we are doing A minus B? By taking 2's complement of magnitude B and adding it to A. Okay. So that will result E as an extra end carry and A. Based on the E bit, I can decide whether A is greater than B, greater than or equal to B, or less than B. Okay, if E is equal to 1, it is A greater than B. If E is equal to 0, it is less than B. So whenever your here itself at this stage, if your E is resulting 1, it means A is greater than or equal to B. It means the quotient will be obviously greater than the specified number of bits available in Q. Okay. See, because already A and Q, two registers are there. We are dividing it by B. Here itself, we got one term as extra one. And by dividing Q by Q, we may get that n minus 1 number of extra bits. So totally, I require n bits for storing my quotient, which is not possible. Here, we are dedicating only n minus 1 length register for storing my quotient. Okay. So if here itself the division is happening with 1, then the available register size is not sufficient for storing your quotient. Hence, I can conclude that as division overflow. So I can stop my division. I cannot perform division. Okay. Divide overflow flag can be set and you can come out of the division. Okay. If E is less than E is not equal to 1, means if E is 0, then A less than B. So I can perform division. I can proceed for the division. Okay. So to proceed for the division, since E is 0, your A is less than B, you should not do this subtraction initially. So I need to restore my dividend back to A by adding B to the result available in EA. Okay, and make the division overflow flag 0, saying that division can possible. Okay, so this statement will result you the previous dividend. Okay, now your A is having previous dividend, right? So first n minus 1 bits available in A are less than B. So hence I have to proceed for next bit. Extra one more bit you need to take, right? See here, since first 5 bits here are less than B, so we are taking 6 bits, right? And I'm again subtracting B from the 6 bit by shifting B right side by 1 bit, so that they will be in alignment and then subtraction is carried out. Okay. So rather than shifting here the divisor left side by 1 bit, I will shift the partial remainder or the dividend which was present in A left side by 1 bit. Okay. So I will lose this term. Okay. So I will shift now A by left side 1 bit. So these are the 5 bits now available in your A, and then we are subtracting B here. Okay, so that is what the procedure. Okay, I will shift left side. See, HL means shift logical left. See, for left shift, whether it is logical shift or arithmetic shift, both are same. Newly added least significant bit, here it is always 0 in any case. Okay, so I am shifting left side by these 3 registers: E, flip-flop, flag, and A and Q. Okay, so that next bit in your dividend is considered for division. Okay, so after shifting it, we are checking the E bit again. So because the most significant bit of your A is now copied to E flag, right? So if E is 0, we are doing it. At any case, we will do subtraction. In any of the cases, we have to do subtraction. But if E is equal to 0, we will be storing. We are doing subtraction, means A minus B. Whatever is the end carry, that we are storing it in E. Okay, if E is equal to 1, we are not considering that E. Okay, see, because most significant bit of your A is copied to E bit, that has to be participated in subtraction. Okay, that bit also need to be participated in subtraction. Okay, to considering that, if my shifted out bit is E1, then whatever it is the end carry, we are not considering here. Here we are considering that end carry, right? So this will say whether the data is 1, I mean A is greater than B or less than B again. Okay, right? So after performing subtraction, we will shift the left side and then again perform subtraction. So A minus B, we will do that. We are doing by B bar plus 1 is adding, right? And we'll check the E bit here, right? So in this case, if the most significant bit is 1, there is no point of going by A less than B condition, because most significant, one more extra bit is available. So obviously A is greater than B only. So one time the divisor can be subtracted from the bits available in A. So Qn is obviously 1 in this path, okay? Because the most significant bit of A is shifted to the extra end carry bit E. So hence your A will be obviously greater than B. Partial remainder available in A is greater than B. So your quotient, first quotient term, it will be divided by 1. The divisor can be subtracted from your partial remainder or dividend by 1 term. So Qn, least significant bit of your Q, is made 1. In this case, if your most significant bit of A is 0, then there is a chance of having A greater than B or A less than B. Okay, so if A is greater than B, if your end carry is 1, it means your A is greater than B. So one time the divisor can go off. So your first bit of quotient is 1. If A is less than B here, it means if A is less than B, 0 at the time only, the divisor can be subtracted from the dividend. So Qn will be 0. You should not change Qn. Qn is already 0 because we have performed shift left. Least significant bit that was shifted to Qn register is 0. Okay, the rightmost bit, because we are doing left shift operation. There will be a newly added bit that was 0 always for one left shift. If it is not 0, we will update it to 1. Okay, no need you to write 0 again in Qn register. It by way of shift itself, Qn will made 0. Okay, right? So your Qn will be 0, right? So still you cannot perform the subtraction of B from A, right? But you have done the subtraction which should not be done. That's why we need to add again the divisor to the subtracted result, so that to get back your original A. This is what called restoring. Okay, you need to restore the partial remainder or the dividend. In the first case it is a dividend, in later on other cycles it is partial remainder, right? You need to restore back to your original value by adding B to A, because we have done the subtraction, but we should not do because your A is less than B. So even here 0th time only the B can be subtracted. You need to take one more extra bit of your A again. Okay. So to go back to this procedure, since one bit of shift has happened, so sequence counter can be reduced by 1. So if it is not 0, again you have to go by shifting left. Now considering the most present bits, again the shifted out bit you need to check, right? If it is 0, then this way. If it is 1, in this way, you can have your n minus 1 qn bits will be updated with what? The quotient values. Okay, so this is the most significant bit of quotient in first case, next case subsequent bit, next case subsequent, till n minus 1 bits of your quotient bits are verified whether it is 1 or 0. Okay, so at the end, as and when SC becomes 0, you will be having your remainder in A, because the subtraction procedure is happening in A register. So remainder will be available in A, quotient is in Q. Okay, so this is the division algorithm, right? So we'll explain this through example, then it will be more clear to you. So before going to that, let us read about the same flow chart algorithm way. So one register to hold the divisor and 2 registers to hold the dividend. This is the basic condition. Usually dividend size should be double the size of divisor. Okay. When the dividend is twice as long as the divisor, the condition of overflow can be stated as if high order half of bits of dividend constitute a number which is greater than or equal to the divisor, okay, the high order half of bits. See, for example, in case of digits, if I take, let us take 80 by 80. Only I am reserving one digit for my dividend and divisor. So, quotient and remainder. 80 by 80. Here 2 bits are there, 2 digits. Here 1 digit length. So one digit for your quotient I will reserve, 1 digit for your remainder. See, check this condition 8 by 8. First half of your digit is greater than or equal to your divisor. So I'll be having 1 here and 0 here. 2 digits I'm getting for my quotient, but I can store a quotient with only 1 digit which can vary from 0 to 9. Okay, I cannot store here 10 in my quotient register. So this is what called division overflow, right? So divide overflow condition will occur if the high order half bits. So to make it easy, I am taking in digits together, high order half digit. Here 1 digit, here I have to take out of 2, first half, first digit, 1 digit. If constitute a number which is greater than or equal to the divisor, if this is greater than or equal to the divisor, there is a chance of getting a quotient which is greater than the dedicated number of bits. Then that condition is called overflow, division overflow. Okay. The other possible conditions are division by 0. If your divisor is 0, if your divisor is 0, then also we can conclude that division overflow has been occurred. Okay. Overflow condition is usually detected when a special flip-flop is set, that is what DVF, division overflow flag. A special flip-flop is dedicated for observing whether overflow occurred or not. If this is 1, it means the result is wrong. Division overflow occurred, we cannot perform the division. Okay. This is a division overflow. Now let us see the example. Okay. So we'll do it by taking a new Word document. Am I audible?
Yes, ma'am.
Yes, ma'am.
So this method is called a restoring method. So why it is restoring method? We will first subtract the divisor from your dividend or partial remainder, right? If after subtraction, how we are implementing subtraction? We are adding 2's complement of your divisor to the partial remainder or dividend, right? If you get an end carry as 0, it means A is less than B, saying that the subtraction should not happen. So we have to restoring the remainder, partial remainder or your dividend by adding B back. Okay. So hence we are calling this method as a restoring method. Okay. So let us consider 2 numbers. First we'll check whether takes 2 numbers. So first number may be plus 433. Assume the dividend as this. And the divisor as minus 13 or plus 30, whatever it is. Anyway, only the quotient sign will vary, right? So what is dividend in binary? 433. Go by calculator. I'm using 433 in binary is 11011 11011 0001. Okay, 11011 0001. Right? 13 in binary 1101. Okay. See, here number of bits are 4. So your dividend should be 4 into 2, 8 bits length. Okay. But my dividend is 9 bits. So I have to take my divisor as 5 bit size. Twice the dividend length, obviously, right? So if I take 5 bits as my divisor length, okay, my dividend should be 10 bit size. Okay. Adjust the first sizes, make it 5 bit size. Okay. Am I clear?
Yes, ma'am.
Why we are adding zeros here? Because we are using registers for storing all the registers of same size, which is equal to n minus 1. Here my n minus 1 should be chosen properly. Okay. See here 5 digits, then I require 2 registers, each of 5, 2 into 5, 10 bits I can store. Because my minimum length of my dividend, the magnitude should not change while considering, right? Minimum dividend length is 9 bits. So to store it completely, I require 2 registers, minimum of 5 bit each. Okay, so your divisor also I'm making 5 bits. Okay, so with respect to this, your A is first most 5 bits, 0, 1, 1, 0, 1. And B is Q, least 5 bits, 1, 0, 0, 1. Okay, and B is 0, 1, 1, 0, 1, which is the divisor. You every time in your algorithm you may require to perform subtraction of B to A from A. So I require 2's complement of B also. So I am calculating minus B also, which is nothing but 1's complement and then add 1, which is equal to 1, 0, 0, 1, 1. This is minus B. Okay. So now proceeding for algorithm, I require the operation, whether it is addition or subtraction or shifting that for that one thing, and E bit, end carry, and then for A and Q, and finally for sequence counter. This is the table I require. So here is E, followed by A, followed by Q, and then sequence counter. Okay, so first operation, what is the first operation? As per algorithm, first what you have to do? See, you need to initialize everything. After that, subtraction you have to carry it out, right? Okay, so initialize everything. E is, let it be initially 0, A is 0, 1, 1, 0, 1, Q is 1, 0, 0, 1, and what is SC? SC is 5.
5.
Okay, right? So what is divisor here? Divisor is minus 13. So in B register, I will store 0, 1, 1, 0, 1. Minus 13. So most significant bit is 1 here. Okay. And coming to dividend, plus 433. This is the magnitude. And plus I am saying like this. So plus is the sign. And remaining is the magnitude. Okay. So only magnitude portions I will take for operations. Signs are stored in another register, another bit flip-flops, AS, which is equal to 0, and BS is equal to 1. Okay, so as per this, your QS, which is the sign of your quotient, XR of AS and BS, obviously it is 1. Quotient is negative, it means, right? So your sequence counter is 1 initially. So first operation is you have to perform subtraction. Subtract B from A. You have to perform subtraction of B from A. So what is, you need to add, it is simply minus B to A, right? Minus B is 1, 0, 0, 1, 1. You have to add this. So after adding, I will be getting 1, 1 means 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, right? So extra end carry is 1 and all the bits are zeros, right? So since here E is 1, it means the result is positive. It indicates indirectly your A is greater than or equal to B. If your E is 1 while performing 2's complement addition, A is greater than or equal to B. See, here itself it is concluded that first half of the bits are similar to B. So what it says, you cannot perform
Overflow.
division. Your divisor is greater than the 5 bits. So I have to set my division overflow flag is 1 and I should stop the division operation. Okay. With whatever are the values that we got in accumulator and A, with that the operation is stopped. Right. See, even if you perform the division with the help of calculator, 433 by 13 is equal to, what are the values? 433 by 13 is equal to 33.3. I have to check what is 33 in programmer. 33 in binary is 10001. I am reserving only 5 bits for my quotient, but I got 6 bits, right? 6 valid bits will gives you the quotient value 33. Okay, so I cannot store this 6th bit in my 5-bit register. So I conclude this status as division overflow occurred and I can stop the division. Okay, is this clear? Next, see the other second case without the division overflow. We'll take dividend some lesser number so that won't occur division overflow, maybe 403. Okay, 403 in binary is 193. So which is equal to 193. Okay, and take the divisor same, minus 13. It is plus minus 13. So minus magnitude 0, 1, 1, 0, 1. Sign magnitude form. Okay. So here also, if I take, this is of 9-bit length, so I should take 5 bits minimum. So 5 bits and here 5 bits. This gives you the valid dividend and this is the valid divisor. Now take the same table with what are the values of A. If I consider A values, first most significant bits of dividend 0, 1, 1, 0, 0 is A and Q 1, 0, 0, 1, 1, right? B 0, 1, 1, 0, 1, right? So here itself your A is less than B. Since it is 12, it is 13. So you can proceed for the division. There is no division overflow flag. Here itself we can conclude. Anyway, next minus B is equal to 1, 0, 0, 1, 1. And the remaining everything is same because AS is 0, BS is 1. So your QS quotient is 1. Okay. And what about the remainder sign? Sign of the remainder is the sign of the dividend itself. Okay. Which is nothing but AS. It is not updated. The same of the dividend sign will be the remainder sign. Quotient sign is XOR operation of AS and BS. Remainder sign is the same as the sign of the dividend. Okay. And now proceed for the same table. So here your A is 1100. So you have to subtract initially B from A, nothing but add minus B. Okay. So I'm adding. So after adding, what are the result? 1, 1,
All ones.
1, 1. Okay. This is the result. And E is 0. It means that A is less than B. A is less than B. So what should you do? A is less than B. First division overflow is not occurred. Okay. Division overflow flag, I will make that to 0. Okay. Since A is less than B, first 5 digits are not enough. So I have to take next more bit, right? Next subsequent bit available in Q should be shifted to A for considering. So ఈ 5 bits sufficient కాదు, 6 bit తీసుకోవాలి. 6th bit ఎక్కడ ఉంది? Q లో ఉంది, right? I need to consider this bit also. So what should I do? I need to shift this to left side. Okay. So but A should contain this value. Because of subtraction, A is updated with this value, right? So I need to restore back my A by adding B to A, right? You need to perform add B to A. Am I clear? Why we are adding? Because
yes, ma'am.
Less than B, you should not perform subtraction. So we are restoring our dividend back by adding B to A. Okay. So what you have to add? B plus B, which is nothing but 0, 1, 1, 0, 1. This we need to add. So 1, 1 is 1, 0. Here 1, 1, 1, 0. 3 ones. One zero, 1, 0, 1, 1, 1, 1, and your E is 1. It is 0. So 0, 1, 1, 0, 0. Is this my A? We got our
Yes, ma'am.
back with the E is 1. Okay. So we'll be getting E as 1 here, and result is after adding 0, 1, 1, 0, 0. Right? And what about Q? Q is same 1, 0, 0, 1. Okay. So this is first phase where we are checking our division overflow condition. Okay. Right? So as per this algorithm, here we got at this stage we were there. After that, we have to shift and proceed for the division. Okay. We should not reduce the sequence counter at this instant itself. Okay. After this, we should shift and then check SHL EAQ, shift left. So whatever is the value in E that we will lose, most significant bit of A now obtained in E, 1, 1, 0, 0, Q 1 bit, and then 0, 0, 0, 1, now 0. So this is what QN. QN is initially 0, right? Okay. This is the first most significant bit of your quotient. We are assuming it to be 0 initially, right? After shifting, yes.
Ma'am, Q is 10011. In dividend, last 5 bits are 100.
Sorry. 1, 1, 1. So this is 1. 10011, 10011. That after shifting 0, 0, 1, 1, QN is 0. Okay. See, if you did single mistake, algorithm output will not be correct. Okay, but the accumulated sequence of operations kada manam okka stage lo okka tappu chesina output raadu, and చేసేటప్పుడే ప్రాపర్ గా చేయాలి. మనం తర్వాత ఎక్కడ ఎర్రర్ వచ్చిందో చూడడం చాలా కష్టం. మొత్తం మళ్ళీ ఫస్ట్ నుంచి స్టార్ట్ చేయడమే బెటర్. మీరు ఎగ్జాంపుల్ ప్రాక్టీస్ చేసేటప్పుడు కూడా you need to be very careful If a single bit change will result to wrong result. Okay, you can't even predict where the error is again. Rather, it's better to restart again. Okay. See, after shifting, now what is the next operation? Subtraction. Subtraction of B from A. So it is nothing but adding minus B to A. Okay, how you can perform subtraction? Adding minus B to A. Minus B is 10011. 10011. You have to add this. Okay, so we'll be getting here 11 is 10, 10 and 1. Sorry, 1, 1 and 1, 0. Okay, this correct?
Yes, ma'am.
Right? So we are getting E as 1 and this result 0, 1, 1, 0, 0. Okay, and your Q is as it is the same 0, 0, 1, 1, 0. So here what you are doing, your E is 1, it means A is greater than 1. Since your E is 1, A is greater than B, greater than or equal to B. So the subtraction can carried out. Okay, it means you can perform the subtraction. Since B, we are able to subtract from A, means one time your B is going from A. So the least significant of your Q, which was 0, now you can made it to 1. Okay. So this leads to your Qn can be made to 1. Am I right? You have to,
Yes, ma'am.
what you need to do, here E is 1. So you need to set the Qn bit. Set Qn, or Qn should be 1. Okay. So keeping everything is same, E is 1, 0, 1, 1, 0, 0 and 0, 0, 1, 1, 1 is your result. Okay. See, here we got this condition, A is less, your E is 1. So A minus B is true condition. Sorry, not this case, right? So here your E is 1, 0. Initially, your E is 0. After shifting your E is 0, right? After shifting your E is 0, you have to go by this path. Okay, and you got E as 1. So I have to make my Qn 1 and reduce the sequence counter. And if it is not 0, I need to proceed further. Okay, this is the path I should take, right? Okay. See, after shift, your E is 0 and after addition, your E is 1. So A is greater than B. I am setting a Qn. Qn I have set and I need to reduce my sequence counter 4 and it is not 0. I need to proceed further. Okay. So Qn is 4 and one cycle is finished. So out of 5 bits of my quotient, 1 bit we have checked properly. Likewise, 4 more bits you need to check. Okay. So after reducing the sequence counter, if it is not 0, what should you do? You again start with shifting left side. This cycle you need, from here you have to start. So the next step, shift left, SHL EAQ. Okay. So E 0 A 1 1 0 0 0 0 1 1 1. Now the next bit we are checking whether it is 0 or 1. Okay, right? So next step you have to perform subtraction. Subtract B from A. It is nothing but adding minus B to A. Minus B is 1 0 0 1 1. You have to perform addition. So once, what is the result? We'll be getting here 1, right? And 0, 1 0 1 1 is the result, right? Any doubt here?
No, ma'am.
Q as it is same 1 1 0. Okay. So here now you have to take the decision since E is 1 here. So it means your A is greater than or equal to B. Okay. Your A is greater than or equal to B, then only your E can be 1. So I have to set my Qn. It means one time our B can be subtracted from the partial remainder. Whatever is available in A, that is called partial remainder now. So the subtraction is true. We can perform the subtraction. So you have to set your Q. So keeping everything is same, 1 is in E, 0 1 0 1 1 in A, Q 0 1 1 1 and Qn should be 1. This is how the updated value of Qn. Okay, after that reduce the sequence counter by 1. So with this, the second bit is also tested whether it is 0 or 1. So 2 bits are over. Now you need to still repeat the cycle for 3 more bits. So after this, you have to shift logical left EAQ. E is 0, 1 0 1 1 0 1 1 1 1. Now the new Qn is 0 for which we are testing. The next is subtract B from A. Okay. So it's nothing but adding minus B to A. Minus B is 1 0 0 1 1. Okay, minus B 1 0 0 1 1. We have to add. So check after adding what is the value I'll be getting. This is 1 1 0 and this is 1 0 1 and this is 1 and 0. Okay, so 9 and here E is 1, right? So it is 1 and 0 1 0 0 1. Okay, so from which you have to take decision. E is 1, so A is greater than or equal to B, this condition. So you have to set Qn. Okay, so keeping the value E same, A same, because the subtraction is true here. So 1 1 1 1 1. So least Qn bit is made to 1. Okay, and SC can be reduced by 1. Okay, since it is not at 0, I have to proceed again. So shift left EAQ. So this 0 1 1 0 0 1 1 and 1 1 1 1 0. Right? Next, subtract again B from A, add minus B, which is nothing but 1 0 0 1 1. After adding, so after adding, sorry, my battery is low. It is 1 0 1 1 1 0 1 0. Right? So your partial remainder is 6 and here it is 1. So it is 1 and it is 0 1. I'm sorry, 0 1 1 0. Am I right?
Yes, ma'am.
Okay. Now take the decision. Again, your E is 1. So your A is greater than or equal to B. So you have to set your Qn. Okay. So E is 1 and the previous value of partial remainder in A is 6 and this is 1, 1, 1, 1, 1. Okay. And SC is 1. Since not at 0, again SHL EAQ. Okay. So after shifting, this is 0, 0, 1, 1, 0, 1 and 1, 1, 1, 1, 0. Okay. This right now won't change. You have to perform subtract B from A. What is B? Nothing but adding minus B, which is 1, 0, 0, 1, 1. This has to be added. So how much you'll be getting? 1, 0.
All zeros, ma'am.
All zeros, yes. So, and what about E? It is 1.
1.
And all zeros. And your quotient? 1, 1, 1, 0. This would not be changed. So here also E1. So the decision A is greater than or equal to B condition only. I have to set my Qn. Right? So keeping E as same and A is leading to 0 and 1, 1, 1, 1, 1. Even my last bit here also 1. It got 1. And my SC is 0. Okay. So now the algorithm is finished because my sequence counter is 0. Now coming to the results. What is A? What is value in A? A is 0. And what about AS? AS is as it is. The previous value of AS itself is your result. Okay. AS is 0 here. So your AS is 0 here. Okay. And what about Q? Q has all ones. And QS is 1, which is XOR operation of AS and BS. And QS is 1. Right? So what is this value in decimal? It is 0. And what is its value in decimal? Apply the
31.
power to power 0 to
31.
30?
31, ma'am.
5 ones. So 31. Okay. So it means reminder is 0 and quotient is minus 31. Okay. Right. So you can check it. 403, right? 403 divided by 13. 31 is the quotient. There are no fractional portions. So remainder is 0. So 403 by minus 13. So minus 31 is the quotient. Okay. Right? Is this clear? Algorithm?
Yes, ma'am.
Okay. So here, actually, we didn't restore anything. If E, every time we are getting 1. If we got 0, then we need to restore A by adding and keeping the same Qn bit as it is as 0 without changing it to 1. Okay. So that case anyway we didn't got in this. You can try for another example where there may be a chance of getting restoring. Okay. So this is restoring method. And there is one more method which is called non-restoring method of algorithm. Only there is a simple change. See here what we are doing in non-restoring method. See here we are doing A minus B. Okay. After that, if your E is 0, we are adding B to it. Okay. So getting back your A. Right. Here what you are doing? We are doing A minus B here. A minus B. If your E is 0, we are adding B to the previous value. So A minus B plus B so that our previous A will be resulted. This is what restoring. Okay. And this A for the next cycle, what you are doing? You are shifting left side. Whenever a bit in a register, if you shift left side, what is happening? It is as if like multiplying it by 2, right? Shifting left is similar to multiplying it by 2. Okay. So shift left A. That will result to A, right? After that, what you are doing? You are doing again minus B. Okay. So finally, you are getting in this loop, for one loop, 2A minus B is the result. Okay. So this is in the what we are doing, restoring of the reminder. So in non-restoring, what they will do means it will perform first A minus B will happen. Okay, right? So without any restoring, they will shift left this. Okay, so shift left A minus B. So shifting left of any value is nothing but 2 into A minus B. So we are doing twice. After that, they will add B. So that gives you same answer, 2A minus B. The final result is the same in both the cases. Only the thing here is, without restoring, in non-restoring method, after performing subtraction, we will shift left side and then we will add B. So that it results to A minus B only. When you have to add B, after shifting left side, you have to add B only if the previous Qn, which will decide whether A is greater than B or not, right? So based on E, if E is 0, our Qn is 0. If E is 1, our Qn is 1, right? If E is 0, you will make your Qn 0 and we will add. Okay. If E is 1, I will make my Qn 1 and I won't add here. Okay. So based on this previous Qn, which is equal to your E, so here whether you have to add this B or you need to subtract this B, that is decided by the previous Qn value. Okay. So based on this Qn value, if this Qn is 1, right? If this Qn is 1, I will add B. If this Qn is 0, I will subtract B. Okay. So in that way, I will be getting the final same value in any method, restoring or non-restoring method. This is non-restoring method. Okay. So whether you have to add B or subtract B in the later cases, that is decided by the previous Qn, right? So this is another algorithm which is non-restoring method, or else you can use a comparator rather than subtractor here itself for checking the magnitudes, and then you can proceed. That is also another method. Two more methods are existed. Okay. So only the thing here in non-restoring method, you need to check the quotient bit every time, whether it is 0 or 1, so that the partial remainder must be restored, right, by adding it or else subtracting B. Okay. So this is about division algorithms, restoring and non-restoring. Okay. In next class, we proceed for other representation, floating point representation formats, with which we can finish our first unit. Okay, in next week, you'll be having a slip test on unit 1, which will be on learning portal. 20 multiple choice questions will be given. Okay, only multiple choice answers. Okay, so be prepared for that, mostly in the next week only. Okay, let me collect the attendance. If you have any doubts, you can ask me meanwhile. 67. $92, $74, $75. $101, $102, $107, $115, $117, $119, $120, $308, now 67. Check all are giving 3 digits. Likewise, you should change your name. So absentees are 74, 75, 92, 101, 102, 107, 115, 117, 119, 120, 308.
Madam, 308 present now.
308. Okay, ma'am. Thank you. Bye for today.
Thank you, ma'am.